in chapter 7. And before I start, maybe we can have a small talks with the Yifans. Yifan recently graduated from Johns Hopkins. Could you please briefly introduce about your research interests?
So thanks for inviting me here. I'm Yifan Du. I recently graduated from Johns Hopkins University from the mechanical engineering department. And my research focuses on two aspects. One is just basically fundamental fluid mechanics on block body flows, vortice dynamics. That's not quite interested in here in the solid mechanics community. And another part basically is data-driven and the machine learning techniques for fluid mechanics, PDEs, and yeah, that's mainly my research focus right now. Yeah.
Thanks. Actually, I'm interested in the fluid mechanics. And
Really?
yeah. And as we know that today, these days, machine learning is very popular in its application for the PDE servers. So what motivates you to do that research? Is it also popular when you start to work on these projects?
So I came across physics-informed machine learning. Actually, this came from some problems, some very difficult problems in fluid mechanics. So, for example, there was what originally encountered was like one problem, so-called sparse reconstruction from sparse measurements. That is, for example, if you have some solution of fluid mechanics equations at certain sparse locations, and you like to reconstruct everything that is happening between these sparse pixels. This is the so-called sparse reconstruction problem, and it happens in a lot of experimental techniques. And so this type of problem can be solved in traditional ways, but it's very difficult to solve. And recently there is a physics-informed neural network, which offers a very easy uh, framework to implement, and kind of it gives also like accurate solutions. This is actually where I started for using machine learning techniques, and it is good. The machine learning techniques, they are often used in like inferences. Basically, if you know part of a physical system and you would like to know the rest of it, and normally this is where machine learning, especially Bayesian inversions, start to come into, and this is where I began the machine learning. And yeah, after the physics-informed neural network, I also developed other methods, and today's topic will be one of the directions that I started. Yeah.
Thanks so much for your introduction, and it sounds to be very promising.
Uh,
As you mentioned, you have just graduated. Will you keep work on your fluid mechanics with the machine learnings, or do you have some other plans?
I will still work on like basically inverse problems in fluid mechanics, but this involves both traditional methods like adjoint variational methods like data assimilations, but also it involves the scientific machine learning methods like Gaussian process regressions, and these are the topics at least I recently got information from. So the new position, these are all the information that I have right now.
Oh, great. Wish you all the best for your career.
You
And
mean
yes,
advices or okay?
yes. And also, I want to ask, Asil has just graduated as a PhD student. Do you
Yeah.
have some advices for the current or the student who is interested to get a PhD degree?
So I haven't gone so far from my PhD, so I will just say what I have on my level. That is, so yeah, as a PhD, we normally just focus on our projects and focus on all of the details and work very hard. I know every PhD work very hard, and so that's normally what we do as a PhD student. But there will also, if you would like to head in towards a faculty position, ultimately as a principal investigator, you might need to start to think about, like, for example, if somebody gives you a huge grant or directly gives you a PI position, what would you like to do, and what's the goal that in your research you would like to achieve, and how does the research that you are currently doing helps to achieve the whole big picture. And this is a question that normally it will take many years to figure out, but many people do not start this early, and until the last minute they go to a faculty position interview and they start to think about, oh, what I would like to do, and that's probably a little bit late. Yeah, this is how I
Yes,
would advise younger people.
yeah. In my first few years, I only think about how to get more papers. Thanks for your advice.
That's one aspect. Actually, that's the one important aspect. Yeah. But
Yeah,
other than that, there are also things that should be like planned much earlier.
yeah, thank you. And maybe now you can share your screen.
Okay. Can you can you see my slides?
Yes. And before you start, I would like to give a brief introduce about the Yifan dues. My name is Yan Rong, and I'm the chair of the USACM student chapters. Today, it is our great opportunities to invite the Yifan to give us these presentations. Dr. Yifan Du recently earned his PhD degree in mechanical engineering from Johns Hopkins University, as he mentioned. And he also has a master's degree in the mechanical engineering from Purdue University. His research focuses on the turbulence simulations, inverse problems, and scientific machine learning, with applications in flow physics and data assimilations. His works has been published in many top journals like Physical Review E, Physical Review Flux, and the Journal of Computational Physics. And he was recently awarded the Mark O. Rabin Prize for the high performance computing, which is a prize awarded for his advancement in high fidelity simulations and scientific machine learning. And thanks, Dr. Deuce. And now it is your screen. I will mute myself.
Thanks for the kind introduction. So everybody can see the screen, okay. So this is a work that I started. I started a little earlier, and around 2020, 2021, and yeah, it is called evolutional deep neural network. So this method can help you basically solve time-dependent PDEs in a way that is similar to the famous physics informed neural network, but with a lot of advantages. This is the first work of this first paper or first part of this work, and it has come a long way, and there have been a lot of things that have been built upon it, and I will at the end of this presentation talk a little bit about recent developments. So many fluid mechanics problems can be formalized as a prediction of the future states or the trajectory. For example, given an initial flow state, how to predict its evolution in the future. Here I'm showing a turbulent channel flow, which is a canonical problem in fluid mechanics with chaotic structures. And if you have an initial condition, how to predict the future, normally you need to solve the Navier-Stokes equations, which I'm showing here right now, incompressible Navier-Stokes equations. It contains a lot of effects, for example, advection, linear and nonlinear advection effects and the diffusive effects. Recently, so this type of flow evolutions can be formulated in a PDE. Basically, du dt is equal to nu is a nonlinear operator. In light of recent developments in deep learning methods, there have been many attempts to predict the flow trajectories using neural networks. So a typical neural network looks like this, I guess everybody knows here. So the input is x1, x2, x3, and output is u1, u2. So basically, there is an input-output relation, and there will be a hidden parameter, which we denote as w. And we can calculate essentially very easily the differentiation of output with respect to input or with respect to the hidden parameters. There's have been a very famous method by George Karnidakis, that is the physics-informed neural network in Brown University. So this type of network, basically, you try to establish a network that covers the whole solution. That is, you have the input of a spatial coordinate and spatial coordinate and the time coordinate, and the output will be the velocity or any solution of this PDE, and you minimize, basically you train this neural network by minimizing this loss, which contains two parts. So one is the physical loss, that is the residual of the PDE, and the other part is some data observation that can come from either inner initial boundary conditions or some like other observations, as long as it gives you information of the solution itself. So the physics-informed neural network basically covers the whole spatial temporal domain of this solution. That is, this is a huge function that covers the whole spatial domain as well as the temporal domain, and you can evaluate this function at any point. So this function will be, you can imagine that if you have a long time trajectory or a larger spatial domain, this function will need to be complex enough to incorporate all of the spatial structures or temporal structures that are developed in the solution. Here, there are certain technicalities, that certain problems of the physics-informed neural network. That is, the pin represents, as I said, the pin represents the whole spatial temporal solution on one single neural network. It's very challenging in terms of the computation and the storages. And also, if you like to know a solution that is beyond this time window, for example, if you like to know the solution that is beyond the time t on the right-hand side, it will be very challenging, and you need to retrain the whole neural network further for prediction. There's a straightforward idea actually. So if we only represent the spatial solution using neural network, and we march this neural network towards the future using governing equation, and this will be the method that we developed, so-called the evolutional deep neural network. So here I'm showing a neural network. So compare this is so-called the evolutional deep neural network, which is different from the PINs or physics-informed neural network in the following way. That is, we only have spatial dependence as the input, and we encode the time dependency inside the neural network weights. That is, the weights are no longer fixed. They are time-dependent functions. Since the weights can change with respect to time, for example, with respect to time, we can see that, since the weights can change with respect to time, it can generate a series of snapshots propagating into the future. And this is what we call as a evolution deep neural network. In this type of structures, you only need to so basically the network looks like this. So you have a neural network that has the weights that are changing a long time, and the change of this solution basically generates a series trajectory, and this trajectory basically propagates the solution in the future. So in this type of structures, you only need to train the neural network to learn the initial state of this trajectory, and once it's learned, the governing equation will help you to propagate these weights towards the future. Basically, you are using the information of the governing equation, and in this way, you only need to have a neural network that is as small as representing only the spatial solution, instead of representing the spatial as well as the temporal solution. You can see that, the network only need to cover the spatial variation of the solution. This is only the conceptualization of the idea, and here I'm going to give some more mathematical details regarding this method. So we still consider this time-dependent governing PD, that is the du dt is equal to nu. We train this neural network. We train a neural network using the initial condition as observations. That is, we only train a neural network that represents the initial state of the solution or the initial condition. And if we like to march the neural network weights towards the future, how do we do that? So if you use U hat represents the solution approximated by the neural network, then the NU must be equal to du dt. That is, so yeah, which is basically the governing equation, and you can decompose this du dt equal to du w dw dt. That is, so w is the neural network weights. The second equality here basically is the chain rule. So you decompose this time derivative using chain rule, and if we have dw dt, that is the time derivative of the weights, we can march these weights towards the future using RK4 or any time integrator you'd like to have. So the problem is becomes how do we know the du dw? Du dw. Basically, if naively you can think that du dw can be inverted onto the left-hand side. Basically, dw dt is equal to the inverse of bu dw multiplied by the right-hand side of the physical equations. So everything in NU can be calculated using automatic differentiation. And du hat dw can also be calculated using automatic differentiation because we can calculate the derivative of the output of the neural network with respect to the hidden parameters. We formalize this type of inversion, so inverse of du hat dw as an minimization problem. Basically, the time derivative of the weights is equal to the minimizer of a loss function, and this loss function is equal to the residual of the PDE itself. So he du dw and the gamma represents the minimizer dw dt minus nu. Basically, this is the residual of the PDE, and we would like to minimize it. It's worth note that du hat dw is this loss function is only with respect to gamma, and everything else is not related to gamma, the time derivative. That is, so this function, this loss function is quadratic. And for quadratic loss function, we know how to deal with it. We can directly, we do not need to do like a gradient descent or any kind of optimizer. We only need to like take gradient with respect to the loss function. This will be a linear system, and we let this linear we basically solve this linear system, this optimality condition, and ultimately we can get the gamma optimal, which is the time derivative of the neural network weights. And ultimately we get this linear system. And at every time step, we just solve this linear system, and we know what is the time derivative of the neural network weights, and we can evolve this neural network towards the future and predict the time history. We did several examples to demonstrate the efficacy and the capability and accuracy of this method. So here, first one is an advection equation. First here, this is the linear advection equation. We can get a very nice solution without too much of decaying, and we can see that the error actually stays very low at a certain level, and does not increase much through 10 time units, which means that the wave has already propagated through the domain 10 times, and the solution is still accurate. We also could consider nonlinear advection equations, for example, the Burger's equation. The Burger's equation gives you shock-like solution. That is, there will be a point where the solution becomes very steep, and the spatial gradient of this solution becomes nearly infinity. And this is a solution that is very difficult to predict, even with some shock capturing algorithm. Here we are showing that these symbols represent the solution itself, and the symbols represent the true solution, and the line represents the solution from our algorithm. You can see that these two match very nicely. And Note that on the right-hand side, there's this small piece of code, which is basically the code that you need to implement uh, for the EDEN method for a different PDE. So you only need to define the right-hand side of this equation, and there's a pre-developed library that you can use, and you just call that library, and you modify the right-hand side, you can directly solve this equation. This is basically, this right-hand side is the only thing that you need to change if you have a new PDE with a completely different form. We also did the tests on the heat equation, which is like a second-order PDE. We get good comparison between the true solution, analytical solution, and the EDEN prediction. And there's we can also take cross sections on 1D planes and look at like the comparison between our numerical solution and the true solution. And on the right-hand side, because we need to take second-order derivatives, the code becomes a little bit more complex, but basically you still only need to provide the right-hand side, which can be easily calculated using automatic differentiation, and that's it. We consider a more complex equation, that is a Kuramoto's efficiency equation. So it is an important example for bifurcation in dynamical systems, but also like it behaves chaotically in some certain combination of the parameters. The solution becomes chaotic. And here we consider this challenging example of a bifurcation. That is, so there's a bifurcation of the solution. If you change the parameter very slightly, or the initial condition slightly, there will be a significant change of the solution. Here we are showing the true solution and the EDEN solution. The true solution is calculated using very high order spectral methods with very high time and spatial resolution. And you can see that these two solutions look even quantitatively very accurate. We also did like Navier-Stokes equations, which is like the center of fluid mechanics problems. We do Tyler Green vortex, which for this type of solution problem, we have analytical solutions. We can compare and calculate the numerical accuracy. The energy decay looks like the energy decay of the EDEN solution compares perfectly with the true solution, and we also have like L2 error to 10 to negative third, 10 to negative 4. So basically, this solution is accurate enough. So it's worth note that there's no pressure in the network. So there's no basically we do not, if anyone knows the Navier-Stokes equation, there's no time derivative of the pressure that is that allows you to merge. So we still could solve Navier-Stokes equation with this method. So how do we do that? So the incompressible Navier-Stokes looks like this. So there's a divergence-free constraint, very much like the incompressible materials in computational mechanics. There's also this momentum equation. So you can see that this system has three unknowns, or two velocity unknowns and one pressure unknowns, which gives you three equations, and there are three indeed, one divergence-free constraint and two momentum equations. So three equations, that's three unknowns. But you see, it seems that there's no time derivative for the pressure. And but in our method, it is required to have a time derivative of all of the unknown variables. So how do we solve this type of system using our method? So the neural network, that neural network to predict the vector potential of the velocity field instead of velocity and the pressure. So the velocity field satisfies the incompressibility exactly by this type of construction. That is, the velocity field U hat is equal to curl of velocity. That is, if you have taken any vector calculus courses. So this is basically the curl of something has divergence 0. There's still no evolution equation for pressure in the incompressible Navier-Stokes equations. Instead, we consider the incompressible NS equations in a different form, that is so-called the projection form. So the time derivative is equal to the projection operator acting on the advection, diffusion, and the body force. So this projection operator is an abstract operator that projects any vector field into the solenoidal space, and basically this is a orthogonal projection. Yeah, in this way, we remove the pressure, the existence of pressure, because the pressure in the incompressible Navier-Stokes acts like a Lagrangian multiplier for the constraint. So here we can safely remove that pressure gradient, and we still have to solve this time marching of the neural network as what we have seen before. So the time derivative of the weights is equal to the minimizer of a loss function, and this loss function looks like this. Now is the residual of this version of a Navier-Stokes equation. The time marching is still governed by this. I'm just repeating the last line of the last slide. And if we do some mathematical manipulation, we can find that we can safely just remove this projection operator and get a new loss function. These two loss functions are equivalent in the sense that they share the same gradient everywhere, and they share the same same minimizer. Which means that basically you can just minimize this loss function j instead of jp, which contains this projection operator. And the mathematical details, I'm not sure if I'm going to cover that. Basically, the mathematical detail here, we proved these two loss functions are equivalent to each other by taking gradient, basically showing that the gradient of this loss function j and this loss function jp are exactly equal to each other. And the trick is that the projection operator is a self-adjoint operator in the L2 space, and you can, because of this, there's a certain mathematical derivation that you can do, which is quite elementary. So basically, we did this type of construction to allow us to solve Navier-Stokes equations using this Eden method, and we indeed got very nice results. So these are the statistical quantities of a turbulent or chaotic Kolmogorov flow, and the dashed line represents the spectral method, and the solid line represents the Eden methods. So these are all the statistics, basically the mean and the RMS velocities. We can see that these two methods give basically very close results. And note that to collect converged statistics, you need to compute the trajectory for a time of 10 to positive 5, which is a very long time trajectory, and this is very difficult, even impossible to reach for traditional physics informed neural network, because in physics informed neural network you need to basically use one single neural network to represent the spatial temporal domain, which includes this long trajectory, and that's nearly impossible if you use a traditional physics informed neural network. And there have been recent developments of this type of method, the Eden method. Today I give like one simple example of recent developments. It's called multi-EDNN. That is, so in the previous introduction of this method, there's a Jacobian matrix that we need to calculate, basically the gradient of output with respect to the weights, and this gradient need to be calculated, which in most cases is a dense matrix, and the inversion of this matrix will be time costly, computationally expensive. And there have been, in the groups that I'm working on here, there is the work that people did zonal decomposition of the solution domain to achieve sparsity in this type of Jacobian matrices. They basically used a discontinuous Galerkin type of flux reconstruction. to couple the solution in different subdomains. That is, for example, if we are trying to resolve this type of rotating vortex, we basically decompose the solution domain into several different domains and couple the subdomains and couple these subdomains together to get the whole solution. And there are a lot. Basically, this ultimately the goal is to achieve a type of discontinuous clerking or higher order finite element methods purely using neural network. And this is one way of one future direction of this EDEN method, and there are other developments. For example, this can be applied efficiently on higher dimensional equations. For example, if you have a PDE of 10 or the 10th dimension or 20th dimension, in this PDEs, normally you would not be able to do anything like finite element and finite differences. Basically, you can only do either neural network methods or Monte Carlo methods, and the EDEN methods have been very kind of successful in higher dimension partial differential equations. So this is the end of my talk, and I would like to take questions.
Thanks a lot for Dr. Du's great presentations. Do anyone has any questions?
Let me ask a quick question. If you had to apply the projection operator in the Navier-Stokes equations in the incompressible case,
Yeah.
how would you apply it if if you were not able to like remove it from the cost function?
If I do not have that cost, if I do not know how to remove it, then I need to do something so-called the projection method. That is, if we merge the advection and the diffusion one step and find out that the merged solution is not divergence-free, then I need to project it to the nearest divergence-free solution. And this projection normally is involved by something so-called projection method, and it involves basically solving a elliptic equation to get the basically the so-called a pressure quantity, and then you do the pressure gradient update of that field to get the divergence-free correction. Basically, this is also how the traditional methods in incompressible fluid community do. That is the so-called projection method. Here we are able to just directly remove it because of a certain mathematical derivation.
I see. So it would be very expensive to apply.
It will be more expensive because you need to solve an elliptic equation, which is kind of expensive.
Okay, thank you so much.
Yeah.
I have a question. As Dr. Du mentions, your weight function W is it depends on the times.
Yeah.
Do you define the weight as a function of time, or does the weight is also you can maybe another neural network of the time?
In the realizations, for example, in our the compute in the code or in the computation, the W is just are just the numbers. They are just like matrices, numbers, and we use we solve this loss function, or you basically solve this linear system and get its update, dWdt, which is also matrices, and we use this dWdt multiplied by Wt. So multiplied by delta t, and you will get that correction, and you apply this correction onto the weights. This is how we do. So W are just numbers. And they are, of course, these numbers are different from one time step to the next. And that correction from one time step to the next step, the correction is covered by these minimization problems.
I see. And so which means like dt will change at a different time.
Yeah, so basically at every time you need to solve this linear system. Of course, for unsteady problems, you need to solve them one way or another, right? Even in finite elements, if you have a time-dependent solution, you will need to do time integration.
So do you have any restrictions for like the dWdt's to make it smooth, or it is fine for any values?
So the dWdt is ultimately governed by the governing equation itself. For example, on this slide, it's Navier-Stokes equations. Normally, if you are updating those weights according to the physical Navier-Stokes equation, the weights are normally fine. But in certain cases, for example, if your solution is kind of weird and your network is very deep, in those cases, there will be some weights that update with very large magnitudes. In those cases, it might affect the stability of this method. And so in those cases, we normally need to, in the solution of this, in the numerical solution of this loss function, you normally need to do a SVD procedure to basically clip away all of those just keep the dominant modes and leave away all of those noisy modes with the smaller singular values. That's normal. That's how we treat it when there are numerical instabilities.
Thanks for your nice explanations. And you have mentioned the advantages of the Edens. And do you, may I ask, do you, at your views, what do you think maybe there is some limitations for the Edens compared to
Yes,
the finite
definitely.
elements?
There is something that in our method that cannot do, that is inverse problems. So in physics, informed neural network is quite flexible. It means that you can give the network observation of any kind. That is, even you can give it sparse measurements, the solution in the future, or any weird observation you can give the network, and it will be able to incorporate those things into the network. But here, we can only do forward problem. That is, we need to know the full initial condition and propagate the solution forward.
Oh, I see. Thank you so much.
No problem, no problem. Okay. Yeah, that'll be it.
Yeah, if no one has further questions, maybe we will end today's seminars. And thanks for Dr. Du's great talks, and it's very clear to us.
Thank you.
And also, if you have further questions, you can send emails to Dr. Du directly. And thanks.
Yeah, thanks. Thanks. No problem. Thanks for inviting me here.
Yeah, it's our pleasure.
Great.
Bye.
Bye-bye.